it's a very complex subject, so kind of trying to mitigate against everything, of course, is very conservative, but it's a very important thing to do. You don't want to black out your entire power system because you have some undamped oscillations occurring. Being a little bit conservative may be a better solution than actually the alternative.
Hello, today we'll talk about increasing complexity in power system studies and the difficulties in achieving compliance. We are consultants from Blake Clough Consulting today, and we'll have a great conversation about harmonics, sub-synchronous oscillation, modeling, and collocated plans, as well as stability markets and tenders. So first to start, why are power system studies becoming more complex?
I think the main big change that obviously we've been seeing in the last few years, obviously the rise of inverter-based resources with all the new renewable generation, drive to net zero. Obviously, this is driving a lot of the reductions in system inertia, more risks of control interactions. And so the requirements of new generators connecting the grid are getting a lot higher, which is driving a lot of the complexity in the compliance process, which I think a lot of people are experiencing recently.
And I think as well, just as there's kind of more experience with these resources, you start to maybe flag more problems as you go along. So both with how the system is changing, of course, with more inverters, but then of course you're just getting more experience with the ones that are already there. So you're maybe starting to see some adjustments with relation to specific problems that you're seeing in the power system. So I think it's kind of a complex subject that's kind of ever evolving as well.
Let's talk about harmonics. So what are the main causes of harmonic non-compliance in modern BASE and wind projects?
The biggest problem that we often see is related usually to resonances between the plant equipment and the external network. So, since the new standard for harmonics came into the UK a few years ago, G55, the study is now looking at impedance loci to represent the grid network rather than developing, the person doing the study developing that external network model. And this is covering loads of different system conditions. So the impedance loci cover varying resistance and reactance values. And so it means that it's very challenging to design a system in which there is no resonance, because often the loci that you're receiving have very like inductive parts of the loci and very capacitive parts of the loci, and you almost connect anything to the network and you create a resonance, especially in parts of Scotland and the transmission system where there's really low damping and low resistance. You almost connect anything and you create a resonance which could amplify the background harmonics. So it's very common with a lot of projects, especially in the transmission level. Even as soon as you just put a cable in, you're now needing harmonic filters. So it's really challenging. And sometimes it can also be the way that the limits are allocated. So if you have multiple projects connecting at the same substation, they allocate headroom to each consecutive project. And so the first project will get half the headroom, then the next project gets a smaller chunk. And then the further you are down in the queue, your headroom becomes smaller and smaller. And so trying to achieve compliance is really challenging. So a lot of it is sensitive to the data you get from the grid.
I think there are some recent wind projects that we've done, and I've seen this particular harmonic non-compliance majorly with the wind projects.
Yeah.
I think the main reason being, we need some reactive compensation there as well, because how long the substations are in terms of when you are connecting offshore wind farms. I think that's again because of the same reason you told about resonance as well.
Yeah. So with the wind farms, you often have a lot of long cables, and that creates a lot of capacitance, and then typically have more like low order resonances, which are more challenging for filtering.
Yeah, I had a question about the challenges caused by harmonic non-compliance, and are there ways to mitigate them?
I think the main way we mitigate those are by using harmonic filters in the network. We do those filter sizing studies as well at Blake Clough Consulting, where we first analyze the system without those filters and see where exactly the non-compliance is occurring, and then we suggest a filter size, we do those filter sizing studies on if there is harmonic non-compliance on particular order, then we design those accordingly, and we repeat those studies with the filter to see if this is plant is compliance or not.
And then once you consider installing the filter, then you also have to recheck your reactor power capability compliance as well, because you're basically adding capacitive reactor power to the network from the filter. And then this might mean you need a shunt reactor to compensate for it if you don't have the headroom there. But usually the main problem with this is obviously having to install a filter, especially for a higher voltage level, in itself is expensive. You need an extra bay. But if the major issue can be that you tend not to get the data that you need to do the compliance studies until quite late in the process. Usually the network operators want to give you the background data, the locali data, only 6 months before your connection date, because they want to have the most up-to-date information on the network when they give you to do the compliance. But then that means when considering the lead time on the filters, if you've already designed your substation, you haven't allocated the space already, or a spare bay, your substation means like a full redesign, you're then having complete delays to your connection. So that's like one of the major downsides of needing a harmonic filter. But so we often would recommend that people, if they think there's a risk, so you can do some preliminary de-risking studies to identify risk levels, but ultimately it's very sensitive to the network data. So trying to push for even provisional data early can help a lot. But generally just planning for it, having space allocated, having a spare bay so that you're not having to kind of go back to the drawing board or realize that you don't have space at your substation if you need one down the line. But yeah, it's not an easy one, unfortunately.
Yeah. I think doing a preliminary study is a good idea.
Yeah.
So that we're at least prepared to have a spare bay.
Maybe one thing is around the data that we get. So another important input on top of like the data you get from the network operator is also the inverter level harmonic data. So it's really important that you get a Norton equivalent model of the inverter. So this is both the harmonic current injection of the inverter as well as like its equivalent impedance at each harmonic order in order to like model things correctly. But to be honest, we see very different data coming from different manufacturers. There's different ways that they're calculating it or measuring this stuff. So a lot of the study comes down to like the reliability of that data.
Yeah.
And that's being provided to us as input from the OEM. So I think there's always some uncertainty there, making sure that the studies and the data that we receive is accurate so that the studies can like reflect the real plant performance as well.
So why are oscillation studies required?
With the increased penetration of IBR resources, we have discussed this in our first part as well, requirements are evolving. We see different events occurring, and then those requirements keep updating, and then we have to update our methodologies as well whenever our generator is connecting to the transmission system. So my understanding is that sub-synchronous modes, I think, have always been existing in the power systems, but with the traditional power systems, those were like low magnitude and were adequately damped. But with increased penetration of inverter-based resources, it's like because of the control interaction, as Caspar mentioned before as well, those we can potentially see that those resources can amplify those oscillations, and instead of damping it, it can amplify it and can cause issues like grid instability, maybe some tripping. So I think that's the main reason that we are seeing in the past years that the requirements related to sub-synchronous oscillation studies have been updating a lot, and like we have quite specific methodologies to perform those studies now.
Yeah, I think just to add that it's actually something that's very hard to do detailed studies with, because if you want to understand how there could be control interactions on the network or sub-synchronous oscillation, you essentially need a dynamic model of the entire network, of all the assets on the network. But obviously there's very sensitive data. So, a new project connecting can't have all the information about the neighboring assets, the dynamic behavior. They don't have those models. So the methodology that NISO has proposed is essentially do the studies from more of like a risk assessment perspective. So it's quite a conservative approach. So then instead of having the information about the external network, you just model the external network as like a Thevenin equivalent voltage source, and then you're injecting perturbations, and it's basically a requirement that the plants are actually providing damping to the network. And just because they're not providing damping, or you have some errors, doesn't actually mean that there will be oscillations, right? But it just means that you're trying to like have as low a risk as possible. But as it stands, only, there's not like wide access to the network models. Although I believe there is work from NISO ongoing where they want to make a system which the consultants will have access to, essentially like a black box model from your point of connection. So you'll have basically access to like the wider network model so that you can actually test the site. So maybe you have to get more data, yeah.
So instead of having those nearby network, it's like a very conservative approach. We're actually injecting, so for instance, there are voltage injection studies that are required to do. So what we do is that at every harmonic order, like let's say from 1 hertz to 100 hertz, we are injecting some voltages, and we are trying to see how our plant respond to that injection. If it's amplifying those oscillations, how is it reacting to those oscillations? So instead of having those black box model at the moment, we are like trying to mimic it in a way that how inverter respond to those oscillations and see. So let's say there are time domain studies under which we see that under this duration there was a injection of voltage, and once the injection, how the plant responds, how it recovers after the injection, and we can see it. We have this frequency domain plot as well, where we plot voltage with plant and without plant, and we see the ratio if it's amplifying those oscillations or damping it, or it has no overall response on those.
I think maybe one point just to kind of follow up a little bit on the discussion on kind of the relevance and why it's becoming increasingly important. With all these inverter-based resources connecting, you're having like different manufacturers, different providers of the inverters. So you're having like a landscape where you have multiple types connecting to the network, different with respect to technology, and perhaps even just between vendors. And what is so challenging about these things is that you have multiple control loops that can be tuned very differently. There's a lot of sensitivity to especially how to the controllers. So then you have multiple plants connecting, let's say in a region, and all of them have some sort of a performance and some sort of a gain and like a phase angle to which they respond to, let's say oscillations in frequency or oscillations in voltage, and intuitively trying to interpret how these things will behave when connected to the system is very difficult. I think that's why kind of we're seeing this very conservative approach to just try to damp essentially all the oscillations you could imagine happening within the network. And it's also very relevant as kind of these are definitely issues that have been seen on the power systems and kind of growing maybe in the last maybe 5 to 10 years, specifically with relation to with wind farms connecting. So I think it's a very complex subject. So kind of trying to mitigate against everything, of course, is very conservative, but it's a very important thing to do. You don't want to essentially black out your entire power system because you have some undamped oscillations occurring. So yeah, it's definitely a very relevant subject, and being a little bit conservative may be a better solution than actually the alternative.
Have you ever done a project for which like we see crazy oscillations, like some non-compliant reserves, and then do we have any example where we have provided some mitigation to those?
So yeah, we've done quite a few projects that have had quite high amplification of oscillations, usually at certain frequencies, and they're usually having to work with the suppliers of the equipment to retune it and try to improve the performance as much as possible. But achieving like damping across the full frequency range is is very challenging, especially for like grid following converters. So it's quite common that at least at some frequencies, usually either side of 50 hertz, you'll have some areas of amplification, because it's not really, it's a very challenging thing to be able to like fully damp everything. So it's more about just trying to optimize the tuning and get as best of a performance as you can. And NISO have shown to be a bit flexible on like what's realistically can be expected and is achievable. But it's more just like a step to drive people to spend a little bit more time thinking about tuning and optimizing the design to basically make the grid as stable as possible. But the major issue is usually the SSO studies comes quite late in the compliance process because you're dealing with the EMT model. So if you start retuning all your controllers, it means having to kind of go back and redo all the compliance studies that you've done previously again, and make sure you're still compliant with like the voltage response, the frequency response, etc. So yeah, the main mitigation is really retuning the controllers, but it can be a bit of a back and forth process. And again, because it's kind of later in the process, it has kind of a timeline risk in terms of like risking energization date, etc.
Yeah, I think this is an important point. When we were in the process of doing compliance studies for a project, I think we can start doing EMT model validation in parallel once we start working with the studies we do in the start, like load flow, short circuit.
So yeah, I think it's something we suggested doing before, which is to like pull some of the SSO studies ahead and do like a de-risking preliminary study so that you get an idea. But it can be sometimes a bit of a difficult thing to suggest, because if you do it and there are no issues, then you're going to end up having to probably do it again at the end because you would have changed something when you do the rest of the dynamic studies. So it may, in times when you don't have any issues, then it's, you're saving time by not doing it an extra study at the beginning, but it could also really help find a problem early. Then you can rectify it early and you save time. So,
and I think it depends also on how soon we get the EMT model from the OEM. If we have the model like in the very early stage of the project, we can maybe start doing EMT validation in parallel.
Yeah.
And then we don't delay SSO much.
Yeah, there's definitely lots of ways of organizing it, and it's hard to always find one schedule.
Yeah, because if it gets retuned, then you have to do those EMT studies again.
Yeah, exactly. So usually you will probably have to change something when you do the RMS dynamic studies and you do the voltage response. You end up tuning like the PI control for the voltage control, and then now your SSO studies you did before have to be redone again. So I think we have kind of suggested that it makes sense, I think, to do maybe a limited number of studies, so maybe not do the full suite, all the SSO, because it's likely you're going to have to do it again, but you can maybe do some preliminary stuff as a de-risking, like a voltage injection for maybe like one initial condition, just as like an initial step to see where the problems are. Yeah. So that definitely could help a lot as well.
I think we can discuss about the scripting we have been using for our SSO studies as well. And I think it has improved the process a lot, because even if the model gets retuned, we don't have to do a lot of like man work. It's mostly about sending the simulations and then, just checking the results back. It doesn't take that much effort.
I mean, the kind of methodology in the studies, if you were doing all of those by hand, it would take a very long time. So I think, having like the automated workflow that we do for our studies and for most of the studies we do, I think is really important. So it does mean that if you have to retune the control and repeat something, at least it's not taking weeks and weeks to get it done. Right. So it definitely helps.
What I've seen recently was some updates related to how those studies were performed. So for instance, we used to do those studies on both minimum and maximum short circuit levels, and now it's like you only need to do those on worst case minimum short circuit levels.
Yeah, I think NISO kind of had feedback on the initial requirements from the V1 version of the guidance, and there was a lot of studies, and I think people were finding it basically too much in terms of like how long it takes to do and the IRSO, and there was a lot of different initial conditions and stuff like that. So in this revised V2, they've kind of narrowed down the number of studies you have to do by quite a lot, especially with the grid following plants. It's something like 8 times fewer, so 1/8 of the number of studies. So it's definitely a lot faster to do now.
And I think they've specified like the type of studies required for each type of plant.
Yeah, so they've also reduced
Yeah.
the type as well. So like the angle in oscillation
Yeah.
projection studies, they've taken out the step response studies.
Yeah,
they've
I
taken
think
out as well.
I've seen there was metrics where they say if you're type AB plants, you just need to do step change. If you're type CD, you just need to do voltage injection and frequency scan.
Yeah, I think it's a bit more reasonable. And there are still other studies that are sort of optional, like the eigenvalue study, which has always been optional, that Will has done some work on.
Yeah. Or there are definitely very many ways you could kind of approach the problem. And of course, it can be seen with the kind of optional parts of the SO studies. Kind of from maybe a more of a system level perspective, if you're kind of thinking in terms of how will it evolve in the future, if you're trying to maybe assess more of the entire network and time, something like eigenvalue analysis, which currently is an optional study, could reduce a lot of the computational intensity of performing the SSO. Then you'll be able to identify potential unstable modes, is what we call them, at specific frequencies fairly easily. But of course, that's going to be very dependent on accuracy of models. These are going to depend on how you set up the models, and they're going to be done in Power Factory instead of PSCAD, which is the normal kind of simulation software used for SSO. But in terms of being able to run through different initial conditions and reducing computational intensity, something like eigenvalue analysis could provide an alternative option in the future, especially from like a system level perspective. When you're assessing loads of different plants, loads of different initial conditions, it can reduce quite a lot of the kind of computational intensity and all the results you have to kind of dig into.
Yeah, and I think the sort of pass criteria on the eigenvalue analysis is quite more lenient. It's a lot easier to comply with compared to the voltage injection studies. So I think it's a good option, but yeah, it tends to come down to the availability of the models. If the models are set up to be able to perform eigenvalue analysis, whether or not it can actually be done.
I mean, how do you follow this methodology with the new updates? So, for instance, for type CD plant, they've mentioned, I think they've mentioned eigenvalue analysis as an optional.
Yeah, so it's an optional. So,
but what are the factors under which we think that, we should consider doing?
It's more a case of like if there's some non-compliance with the mandatory methods.
Yeah. Okay.
Then you can basically do the eigenvalue analysis as like further evidence that it's actually okay. And that if you can show that you're complying with the eigenvalue analysis, then you're sort of like more inclined to allow you to proceed without having to retune your control or make significant changes.
So thank you very much to all our consultants for this really interesting discussion. And if you have any question about those topics, please reach out to Blake Clough Consulting.